this is a Rust project that is part of the company called Polymath, and this company is quite interesting. So it is a blockchain project, but as I'm going to explain, it's not. It belongs to a certain category of blockchain projects. It's more oriented towards industrial applications, like financial, within the financial industry. This is Polymath is a Canadian company, but we have developers all over the world, so it's quite interesting place to meet people from different backgrounds. But all of the Rust devs are very strong in Rust, and it's quite quite an interesting place to learn new skills as Rust is concerned. In the talk, I will first explain or try to just introduce securities and their financial securities and their relationship to blockchain. I will go through some basic stuff about Substrate, which is the framework on which the project is built, and I will tell how Substrate in fact enables some advanced software engineering practices. Then I will talk about the Substrate in more detail, specifically in the context of our project. So how Substrate applied to the project yields this application that we're building. Then I will explain some code that I will show in the IDE, some specific fintech specific processes such as settlement, and also I will briefly talk about confidentiality, which is a special feature of our application. And then, yeah, we'll just briefly talk about smart contracts, which are implemented, which are just the WASM, but it can be any WASM, but there is a special DSL written in Rust for building those smart contracts. First, about blockchain securities and securities in general. So why this project? So why is it important? Securities correspond to a very large class of financial assets, and if the blockchain community is very forward-looking in terms of bridging the gap towards the legacy markets and trying to monetize some possibly illiquid assets and tap into the traditional finance in general, so make it more digital and yeah, apply blockchain techniques to it. Securities are defined as tradable financial assets. And sometimes we say that securities are fungible assets, which means that you can take, you can substitute an amount of this asset for an equal amount of this asset, and the result will be the same. So they are not distinguishable from one another. And the categories of securities are equities, debts, derivatives. And when we talk about derivatives, I will explain later that this is a very interesting and it's kind of a tricky and interesting target for software development, because there are at the moment there are lots of companies that work with so-called DeFi, which is decentralized finance. Our company is not related to this, but on the blockchain, derivatives can be represented very easily, in a sense that it's easy to write a program that respects certain conditions under which payments are made between parties, and it's quite an interesting possible application for blockchain. Securities are also very regulated, and there are usually national level organizations that regulate how securities are traded, and this presents often this presents a barrier for startups to enter this sector of the market, of the financial market, because companies need to be fully engaged into interaction with those agencies, and Polymath is engaged. So this is an example of application of securities to like a common scenario where we have a startup, and the startup at the present moment is owned by its founders, and it's interested in raising capital. There are several options how to raise the capital, and all of those options involve securities. And in the first option, the startup goes through a regulated process and makes an initial public offering some shares to potential investors. In the second option, it offers shares without going through a regulated process privately. But in all those cases, the founders grant some control of the startup to the new investors. And there's a third option where they offer some so-called convertible notes, which are just agreements that the founders will issue some shares to the investors holding those notes at some later event. And this is an example of a derivative because it's not entirely equity. So it's like a programmatic, it's like a smart contract because it can be implemented as one. There's just a funny example of a derivative. If you know, there's a cryptocurrency derivatives exchange, and they used to have a token for you could bet on whether Trump or Biden would become president. Before the results were announced, they had a token, which, well, a few tokens, and it was quite funny to see how the predictions changed with when news would come out, and yeah, it probably started from Trump being the first candidate, and then gradually the value of the Trump token decreased, and yeah, eventually it became zero. So this is a derivative because it depends on a future event, and in case of a positive outcome, the derivative, the issuer of the derivative pays a certain amount of money to the holder of the derivative. Regulation is important because as I just shown, this Trump Go token, apparently in the UK, it's forbidden for companies like FTX to sell such derivatives to retail customers because Financial Conduct Authority ruled out. So they FCA decided that it shouldn't be legal for retail consumers to use derivatives, and that's why in the UK it's not possible, as far as I know, to invest into Bitcoin exchange traded funds as opposed to the USA and some other Scandinavian countries and probably German speaking countries. Just an example or illustration why it's so this, yeah, I would need different. Can I still see my screen? So I think.
Yeah, we can see your screen.
Okay, anyhow, I will just skip this slide because yeah, I was going to show it in a browser, but just at the top we have the so-called market capitalization of cryptocurrencies, and well, it's quite small, so it's a few $100 billion, and here at the bottom, this big chunk is the derivatives market, is the world derivative. So there are in business terms there are reasons to try to to bridge to the legacy finance because it has so many assets on it, and working with securities is more complex than just working with peer-to-peer transactions, as we know from the basic cryptocurrency applications, because securities should match the structure of financial institutions, which include different branches such as front office, middle office, and back office that perform different functions, and they allow to execute complex instructions, and yep. So moreover, they allow regulators to audit trades, and they allow services like custodianship and so on. So this is an illustration of the settlement process. We on the left-hand side we have the entity that wants to purchase some securities, say stocks, and on the right we have the another entity that is going to sell those securities. In the middle, we have the stock exchange where the securities are traded, and clearinghouse, which implements the payment transaction. And also we have the participants like central securities depository, where the securities are physically held. And on the side, at the top right corner, we have the regulators, which somehow oversee the processes and sometimes intervene or perform audits. And so the idea is that the whole settlement process as implemented in the blockchain application should be transparent for the regulators, and it should be it should conform with the current requirements that are that exist in the industry. Now let's go to Rust. Substrate is a framework, and I would say it's an opinionated framework for building blockchains. It consists of multiple layers, so it takes care of all the networking. It has the consensus engine. It has the queue that manages transaction ordering. It has the database which stores, well, at the low level it stores key value pairs, but it's very optimized for applications in the blockchain runtime. And it also Substrate also provides at the highest level a state transition function, so that you could view a Substrate applications built on top of Substrate as say state machines, which given a previous state and will produce a deterministic next state if according to the transaction or transition. So you interact with the application by sending transactions, and those transactions transition the state from one from the previous state to the next state deterministically. And another feature of Substrate is that it allows upgrades on the fly without stopping the application or the network. And I will explain later how this is done. Sorry for this slide bug. So the architecture of Substrate is the following. So we have the runtime, which consists of so-called pallets, and there are a number of pallets which are pre-built. You can import them from Substrate from Substrate crates or from Substrate GitHub. You can also modify them, like you can fork them, or probably you can just copy and replace some parts of the modules. So pallets are essentially crates in Rust sense, but they have very specific internal structure, which I will talk about shortly. So runtime is the level where application programmers mostly work, and other layers like system or support library, they are somehow the support library is kind of given, so you cannot change it without forking Substrate. But yeah, there is some work still on the node on the client application, because you need to configure how the runtime starts, especially in, at the point where the whole blockchain starts. So it's at the genesis. So you have to configure this moment where the application starts. So about the contents of a pallet, so we have a Rust DSL, which is implemented using procedural macros, and it's one of the reasons why Substrate is opinionated, because by implementing it is as a procedural macro, you kind of lose some performance at the compile time, because it's obviously it takes longer. But on the other hand, you have this very regular structure. So every pallet, every substrate pallet has this structure. It may or may not have some bits like errors or events. You may skip having errors, events, but normally you would have some storage, and you would have some you would have the module declaration, which contains functions which are called extrinsics. So the idea behind this is that extrinsics are they represent function calls that can be made from the say from a web application, from Web3 application, and they can be dispatched to the runtime, and the runtime will perform this transition from the previous state to the next state. So they are in fact state transitions. So here is an example pallet. Let's say we want to store a U64 value on the blockchain. When we store that value, we emit an event. Event is just a notification that Web3 applications can listen on, and they can record the event or take some actions based on received events. And also we make this value public for anybody to read. And there's a function that allows to retrieve the value from storage without modifying it. So again, we have the in the pallet we have the definition of this so-called configuration trait, which is just trait with capital T. So this is something that that is common to every pallet. And then we have a declaration of the error in just in our case it's just one error just for illustration. And then we have an event in containing the event which we emit when we store the value. And then there is this storage, which is it's quite an involved DSL. I think it's modeled after the Solidity language, which has a similar syntax for defining maps, for defining types of map. So yeah, so just we have the interesting bit is we have a map that stores mappings between account IDs and U64. So for a given account ID, you have a U64, and the syntax of maps in Substrate is that it always every key has a default value. So the value must have a default instance. So if you if you don't actually have some mapping in storage, and you ask for the value at the key that is missing, the getter function will in fact return 0 in this case. So this is the total semantics. And the module declaration contains this extrinsic function, which is, again, as you can see, there is a DSL which has this origin parameter, and the origin is the caller of the extrinsic. So it can be an account ID, or it can be some system origin, such as root. There is a special there's an example of a system origin. So yeah, so in the function we first deduce the sender account ID from the origin, because if it's an account ID, the ensure signed function will return the account ID, and if it's something else such as root, the ensure signed will return an error. In this case, the extrinsic will just return, and we won't have anything done to the storage. And here we just check that the parameter is not 42. So if it's 42, we will return this error in invalid parameter. Otherwise, we will change the value in storage, and this deposit event function emits an event. Let's talk about the runtime. Let's start with unit tests, as if we are doing test-driven development. So based on the palette that I've just, on the example palette that I've just introduced, let's design a test which sets some value, checks that this value is set in storage, and then it tries to do something that should return an error. And for this, we have some helper assert macros, and we have to define a test runtime. So basically, it's a mock runtime. So this is the runtime on the right-hand side. It's not very long. Again, we need to instantiate this test trait, test configuration trait, and because the test trait instances frame system trait, we also instantiate this frame system trait, which actually configures the substrate internals. And then, yeah, we define example as a module with test trait as the parameter, where module is the module defined in here. So that this is module. Yeah, basically we execute the test with default Genesis config with some configured storage, and here are the assertions. And so we set for the account 1, we set the value to 100, and then we check that the value at the account 1 is 100, and then we try to set the value to 42, and then we get the error this is assertion checks that the result is the error, this exact error, and also assert no op checks that the storage hasn't changed. More about the storage. Storage is implemented at different layers, and application developers work with the storage API. But also there is some sort of optimization for state transition functions, which may roll back. So there is caching when the transaction is computed, and once it's computed, the cache is committed to storage. At the bottom, we have a virtual Merkle tree. It's Merkle Patricia tree. So it's a tree where every node has 16 children, and it's a prefix tree. So we store keys in lexicographic order. So when you want to retrieve some value, you follow path along the tree, and here is the value. Values are stored as vectors of U8, as byte vectors, and keys are 256-bit hashes. And well, it's just a virtual structure, because at the very bottom we have just a key value RocksDB database. So then benchmarks. Benchmarks. When we talk about benchmarks, let me say that the runtime can be one of three compile targets. So it can be interpreted WASM, it can be compiled WASM, or it can be native. And if it's native, it's just built into the node client, into the Substrate client, and you cannot change it without stopping the application. But the nice feature of Substrate is that you can swap the compiled WASM at runtime. I hope I will show this shortly. Benchmarking framework uses a lean regress crate and makes an assumption that all the functions, all those extrinsic functions in modules are linear in complexity with respect to their parameters, because it does make sense in that on a time critical application, especially if you have rather slow running WASM code, it doesn't make sense to have functions that are, say, polynomial, because if they take too long, then block production breaks. It needs to be every so often, so it needs to be synchronous. Yeah, so there is math behind it, and benchmarks again have a procedural macro associated with them. So there is in the macro we give some we set the benchmark, and this setup is not measured, and then we can make a call that is measured. So the start time and end time is measured by the benchmarking backend, and then it follows by a non-measured verification block that checks that we arrived at the desired state. And this is an example of a benchmark. So this is a benchmark, and so this is a command that runs the benchmarks. This is a so-called identity palette, which is part of Polymesh, and we run it with make 200 steps when selecting input parameters, and repeat 10 times for every step to double check the results and reduce the error. And we specify the type of compiled artifact. So we test compiled WASM, and the output of this is a so-called wait function, which is used in order to define how much time the call is going to take. So because we cannot just execute the function and wait until it finishes, because if it takes too long, then block production cannot continue. And in order to eliminate the possibility of such events, we simply define a wait in advance, and there is an option to refund some. Say if the function used less time than than the wait function initially reported, then we can refund part of the cost to the caller. So wait is basically, you can say it maps to some fee on the blockchain. Let me, because I'm probably over time, let me just show you how we can upgrade the runtime. You can see this application. It's Polkadot.js. So this is the JavaScript application for working with Substrate blockchains. So we have some functions here. So in order to upgrade the runtime, I will. Let me show you. Say in the Explorer, we'll just let's have a look at the workings of the blockchain. So it has 5-second blocks. So every 5 seconds, a new block is produced, and there are some events that are emitted when something happens on the blockchain. Some extrinsics are called, and you can see in here you can check the storage. So let's check the timestamp. For example, this is a value which is stored in runtime storage, and you can also call some functions, extrinsics, and because upgrades can be implemented as a pseudo function, I will just take a shortcut and do an upgrade using pseudo. I'm copying the whole upgrade here. It's quite big, so it's 4 megabytes, and this is the WASM runtime, which contains all the pallets. I will override the weight because the runtime is too big, and basically when the when you try to upgrade the runtime without override, the application will complain that it's too heavy and it doesn't fit in a block. But in fact, it does. It just it doesn't. The runtime doesn't depend on the length that much as opposed to what the weight function computes. So it weighs the upgrade too heavily. So now that I'm bad signature. Okay, that's interesting. Yeah, something didn't work as it happens. I can try another binary, but just not to take too much of your time. Basically, this is one of the ways to to upgrade the runtime. So in the end, when the runtime is upgraded successfully, the network just continues as if nothing happened, but with the new runtime. And you don't have to stop the nodes and restart them. So just a very straightforward process.
Cool. Anything else that you wanted to?
Well, let me just finish with some facts about the project. We have, as I already told, we have developers from different countries, and it's a very vibrant environment with some very talented Rust programmers. And the idea of choice is Visual Studio. Some people use VI or Emacs. Actually, one person uses VI, and I use Emacs. We use Rust Analyzer for semantic analysis and for code navigation. It builds quite well into visuals, all the IDs. So Visual Studio, VI, Emacs. It's possible to interact with Rust Analyzer. Then on the developer build side, there is a little bit of a problem with the procedural macros, because there are so many in Substrate. You cannot get away with not using procedural macros, because when you define a new pallet, you use all those given macros to construct a module. So we need some sort of infrastructure, which we implemented using Cargo Remote, and we rent a server on Hetzner, and also we installed SC cache locally on every account on the server, and that helps with speeding up the build time. And yep, so let me finish on this fancy chart. So you can see the Polymesh project features in one is one of the top 20 active projects on GitHub. The first one is notably Cardano by wide margin, followed by Ethereum, Polkadot, Kusama. Some of those projects are based on Substrate, like Polkadot and Kusama. They are Substrate based. So this is, I think this is it.
Thank you very much.
Thank you.
I'll just stop recording.